Okay, so another day, another stream. So today we'll be talking about something called ISLE, which is basically an acronym for it's ISLE or instruction selections or lowering expressions. This is, you can think of this as firstly a continuation of the Cranelift exploration that I've been doing. And this part, this is one component of Cranelift. It's a very important piece. So we'll get into the details of this. Actually, let's just jump into it. So what ISLE does is, in the previous stream, we talked about Cranelift IR, being very similar or pretty much serving the same job as what LLVM IR does when you talk about the LLVM backend. In this case, ISLE is what we use to effectively take Cranelift IR and lower it to machine instructions. Not all the way to the actual binary that's going to be output, but machine instructions. It's pretty much a mapping from the IR level to machine instructions. Now, first question is obviously going to be, why do you want to do this in another language? This is supposed to be all Rust. Uh, so yeah, at least in this stream, because it's going to be very short and crisp, so that I can come back to this when I'm if I lose track of the whole work that I've been doing on Cranelift. But effectively, those design decisions are something that, there's a very good link to it. Uh, Let me see if I can find it. Yeah. So this is a good blog, talks about Cranelift's instruction selection and DSL and why they need it. So pretty much there's like three reasons apparently. One is if you were to actually write this by hand, that means the lowering or the mapping from a higher level IR to a lower level machine instruction, it can get really, really long. And I'll show you a couple of examples of that. The other stuff, it's always going to be things like that also sort of, if it's going to be very tedious to write, it's also going to be very tedious to refactor and change. And also, you could introduce a lot of bugs into it and these bugs can be subtle. Uh, so why not leverage you know, something that's can address these problems? That's how I'd put it. So if you just, go up one level and write this in a different language, which we'd call ISLE in this case, which has a number of things like it's got types. So it's a statically typed language. It's actually a language for the first thing. Um, and that should allow us to effectively, you know, avoid a lot of the mistakes that you would normally make, including subtle bugs, etc. Uh, that's kind of what I guess the um, this blog sort of mentions. It's like, we can pretty much use this whole strongly typed abstraction in the DSL. And then there's a bunch of things that this DSL allows you to do. But the first thing that I wanted to say is, what is a DSL? When we talk about it, at least in this context, it's a domain-specific language. Um, in ISLE's case, I'll just limit it to that discussion because domain-specific languages can do a lot of different things. But in our case, which is ISLE's case, what does it do? As you know, it converts Cranelift IR to machine instructions. How does it do that? Well, basically, uh, you write your rules in a form like this, which is, where did that go? Yeah. So this is an example of the ISLE, language. So you write your ISLE, code in this manner, and then this will produce a file like this, which is uh, let me see if I can show you the comparisons. Actually, it's going to take a while. Oh, correct. Um, yeah. All right. So so if we write our IL code, that will produce effectively this particular Rust code. So at the end of the day, you're still writing Rust, but you're writing Rust using a meta language that will be compiled down to Rust, right? So the first thing I want to say is all of this stuff that you see here, which was saying you define rewriting rules that maps input terms to output terms. That's exactly what IL does. But the way these rules get compiled into Rust source is very interesting. It's basically you'll be able to see the Rust source, the types, etc., and you'll also be able to see the fact that all of the mappings that we're doing, effectively, we'll use a lot of um, matching expressions in Rust. So rather than you write that by hand and you write a whole 100 or 200 of them, for example, uh, let me see if I can show you that as well. So you've seen that this is the enum that's generated when you write the same thing in ISLE that produces this. But if you were to write something like a constructor in ISLE, which is, let me find the first constructor. It's yeah. So this is the constructor. Uh, it's at line 414. It's called FPU op with whatever the name is. So if I just look for that, I'll find it here. So you can see that this particular function is already mentioned over here. Um, well, this is part of an external constructor, so we don't have an implementation for it. But in any case, I'll come to the external constructor versus the regular constructor. But effectively, this is a function that has been defined for you that will do the lowering part from your machine learning, your higher level IR to your machine instructions. Sorry, I said machine learning to cut off with that. Um, anyway, so this is an example of that. And you can see what I was trying to say was this part. Okay, it's not showing me the match expressions that I wanted to see. Mhm, mhm. Oh, screw it. Let me just find one. Yeah. So pretty much you'll find a lot of stuff like this. Okay. You write a lot of stuff like this. Instead of you writing all of this stuff, uh, you can pretty much use IL to get it done for you and reduce that amount of complexity that you'd have to deal with if you had to write all of this by hand. In fact, a lot of stuff can go wrong. So a better example would be if I showed you something like, say, I add, all right? So just look at this. I mean, this is a simple constructor, all right? And this thing can easily get really, 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 really long, right? You don't want to like sit and write this by hand effectively. And you can see some of these match statements can actually go into hundreds of lines, or rather 200, 300 lines, etc. It's going to get really tedious, and it doesn't make a lot of sense for us to be writing this directly in Rust. So you can use a meta language and write that over here. And there's actually a second goal as well with ISLE, which has to do not with just lowering, but also being able to write optimization rules. So this is specifically for lowering from the higher level IR to the low level part. The second one, we're not going to cover right now. I'm just talking about this because I'm working on writing a backend. But yes, that's also there. So that's one part. Then the second thing that I wanted to show you is exactly, let's try and make sense of ISLE a bit. And the best way to do that is they've got a very good README page. All right. So you can sort of skip everything else. Uh, actually, you know what? I'll show you something very that sort of gives you a mental picture of what's going on. So here's what's happening. you write your IL code, which is your source IL source code. It actually gets compiled down to Rust source, and there's an implementation for it in Cranelift. Where is that implementation? You basically go into Cranelift, and then you see IL. This is the implementation for it. Uh, the entire implementation's in here. So you've got the source code for that, the whole, the lexing, the parsing, the whatever is mentioned over here, you know, the analysis, the try construction, all of that is done in this part. And then there's an actual IL compiler called ILEC that actually does, it's not much, it's just a one-line thing. It's just a simple executable that calls on the IL implementation to effectively do the job of taking in the IR and producing the Rust, the equivalent, sorry, taking in IL code and producing the equivalent Rust code. And we can look at an example of that. Now, obviously, I don't think I can cover everything, but just so that I have enough of the basics, we'll not go into things like, what's a pure, IL function and what side effects are, etc. I'll touch upon that, but just basics. So here's an example. Like when you say type I32, primitive I32, you're basically saying declare that we're using the I32 primitive from Rust. And here's the main important thing. Here's something that where we're trying to say, this is a high-level instruction. It's an enum. So it can have any one of three variants. It can be an add, load, or a constant. And then there are various, uh, you can say the associated data that this particular variant can have, just like in Rust. It's obviously modeled after Rust. It should be sort of evident over there. And then you can have your own types, whatever you want to sort of declare. And then types can be composed of types, further types, which is, for example, address mode. Where's that? There should be an address mode. Yeah. So a low-level instruction can have its own enum with a couple of variants. So effectively, the example is going to talk about how do I take a high-level instruction and map it to a low-level instruction? Because that's exactly what IL does. It lowers from Cranelift IR to low-level IR. Sorry, low-level instructions. So when you write this stuff, and then you also write a declaration like this saying, okay, I want to instantiate a function called lower, which takes in a high level instruction, produces a low level instruction. And then I'd say, okay, if this is going to sound very functional programming like, because there's quite a few concepts in there actually from functional programming. You can say high level instruction dot const, which is high level instruction dot const. It should produce, if you're given that, you just map it to the low level instruction const, whatever the corresponding low level instruction is for that. And then I pass this on to the compiler, the ILEC compiler. It's going to pretty much produce this code, right? And if you see very carefully, this is actual Rust code. It takes a high level instruction as argument. It returns a low level instruction as an option. And then if you look at the implementation as well, it's basically an if let statement. It says if let constant, high level instruction constant is the pattern that you've provided me, which is basically the argument that's been provided. Then just return the low level instruction corresponding. That's it. Something that's more interesting is this is what I was going to talk about. This is great if you're basically trying to model your machine's instructions um, and effectively map them from a higher level representation to a low level one. It's great, but this may not be sufficient because you may end up doing a lot more work if you try to do everything in IL. So IL provides a way to actually add arbitrary logic to whatever IL produces. So IL can produce the Rust source that you just saw. But what if you want to externally provide your own arbitrary logic to do XYZ things in certain situations? You don't have to come up with a syntax and a way to do that. You can simply go ahead and put that in something called the context, right? And you can have your own implementation. For example, this is a function called put in register, and that should effectively go ahead and uh, I'll show you what I mean. So you saw that, we had a declaration. Sorry, where's that? We had a declaration, a simple one. We've declared a function called lower, and we've attached a rule to it. Likewise, if we were to attach another rule called lower high level add to a low level add, and then also attach a high level load to a low level load, which is sort of what we were doing. And then the way you actually do the add and the load is you're going to need a way to express the fact that you want to put a value in a register. And that's something that you could not express in, just using this part, right? You couldn't really do that because you might have an arbitrary way of doing those things. So if you just declare a constructor called put in reg as an external constructor, it will go ahead and say that, okay, I'll just go put that method in the context, right? And you get to implement that in actual Rust code. So, but before I just show you the actual implementation, I'll show you what happens when you do that. Now, when you look at construct lower, it's going to produce everything for all the three different patterns that we've got. We're not using an iflet anymore because we've got three variants. We can match all of them. It's a constant. We do the same thing. If it's a load, we basically do the mapping, but we also use the put in register external helper. Likewise, same thing goes here for add and load. Now, and this is it. This is pretty much what's actually happening with ISLE. What I wanted to do was also sort of talk about how this is working at the Cranelift level, right? Because that will make more sense. For example, if I go look at Cranelift, and if I look at something like in CodeGen, I'm looking at the instruction-specific architecture part of this. And let's say I'm looking at risks 64. So forget the risk 532, that doesn't exist. I'm working on putting a backend together for that. Hence all this stuff. Okay. So if you see this is the actual entire RISC-V 64-bit backend, the ISA implementation for it written in ISLE is all here. And it's about 3,000 lines of code over here when we talk about just the instructions alone. And then there's also an ISLE for lowering, like whatever you saw, right? This is exactly what's happening. Whatever you saw previously, that's exactly what's happening in this file. The RISC-V 64-bit instruction selection, that is clif to machine instruction lowering, is happening using this file. For first defining all of our possible instructions, the formats, the instructions, all of that stuff is sort of declared over here. And then this file does the lowering. Where does this all happen? So the way this works is we actually have a build script wherein is that this is very much like a regular Rust project where you might have an extra build step where you want to do a couple of things. You want to produce a couple of macros maybe, or expand a couple of macros before you compile something. Very similar. You can see that there's a build script over here. This build script is what actually compiles the ILEC compiler and then hands the ISLE code to that compiler so that it produces all the ISLE files. And those files actually sit in the target directory, which is here. And debug, build, look for Cranelift. You'll find it here. Okay. See, all of your final artifacts for each of the architectures that you want, all the rules and the lowering pieces are all bundled up into one single file. They're all here. In fact, The ISLE compiler is pretty nice. It actually tells you what goes, all the different ISLE files that went into producing this Rust source module, which is there's the prelude lower, there's the actual instruction.isle that I just showed you, which is this one. And there's the vector one is, it's just the vector instructions. And then there's lower as well. All of this put together produces this. And as you can see, the first thing that you'll see is the context rate. So all of this stuff is not implemented in this module. It's provided by us. That's the programmers, whoever's written the backend. This is stuff that is provided as arbitrary logic outside of what ISLE produces. So for example, if I am okay, I'm inside this, so I may not be able to do that. So if I was to go in here and look at ISLE over here, I should be able to see a lower folder, and I should be able to see my context rate implementations here. Let me see if I can just do the comparison. This is ISLE here, right? So I just want to find anything, just like it's unique enough. So let me see if I can find it. It's not in this file. Yeah, the ISLE 564-bit file that you just saw, that gets included over here. Where's the implementation for this? Now, what? Let me just do this. Mhm. Okay. Great. It's in a macro somewhere inside ISLE common prelude methods. So there is a particular common shared piece of implementation. It's in there. And you'll be able to see a lot of this stuff similarly. Let me pull that again. I want to see something that's RISC-V specific. Here's a better way of doing things. Let me go to low, not this. Sorry, jumping around too much. So let me say, I look this one up over here. Yeah, see, this is a constructor that's provided. This is an external constructor that's provided to us that we didn't have, and the implementation's right here, right? That's it. So that's the build process. So we're not doing much because I was trying to learn TableGen for a while, and I'm like, okay, yeah, that's not working. This stuff is pretty straightforward. You don't need to recompile stuff, etc. The moment you add new ISLE rules and then you recompile, that should be sufficient. You don't have to make changes elsewhere to make things work. All right, so that's the last piece. I've covered the context trace, the build process, and the folder as well, and the README, and a brief overview of the constructors, the external constructor. There's also something called extractors, etc. In the interest of time, I'm not just going to go through all of that. But yes, there is a very nice reference guide over here. Pretty much, it talks about the entire ISLE spec. We can look at it. There's a whole bunch of things, like I mentioned, things like, pure expressions. Sorry, wrong place. Things like pure expressions and side effects and yeah, sorry. Okay, that's not mentioned here. But effectively functions that have side side effects are stuff that are yeah stuff that could go do some modification of a register, etc. Which maybe when we go through this, we continue this Cranelift stream, we can talk about a lot more of that. But yes, it's very interesting to see that, Cranelift is actually leveraging quite a few interesting concepts, I would say, to build a robust code generator. This is not just a hobby project, definitely. It's a lot mature. It's very mature. It's thinking about a lot of different things. There's also something called eGraphs, which is again sort of a term rewriting thing, but it is very different. It's used in the mid-end optimizer using what's called equivalence graphs or equivalence classes, etc. Maybe that's for a different discussion when we get to it, because the first thing I'd like to do is actually figure out how you would write a backend. I have a I have a basic understanding of how we can put together a backend, but since the backend that I want to write is 32 bits, a 32-bit backend, there's no example for that in the Cranelift project. We'll have to work through things as to how how we can make that happen. But yes, that's about what I wanted to cover. It's very, I mean, it's pure, a lot of theory, not a lot of code and stuff. But just understanding how this thing works, the pieces are put together, sort of very interesting, so that we don't get lost and jump into a lot of other places. All right, that's about it for this stream. Thank you. Have a good day.